heard quite a lot about already, and in particular the bits that others haven't covered. Mike, to you.
So thank you, Costas. So I think you've already heard about multi-level methods for reaction networks from Dave, from Des, and from Ruth. So as it says, I'm going to try to cover the bits the others haven't covered, but first I'm going to go back over the basic ideas and give you the opportunity, if there are things that weren't clear with the fundamental ideas, let's make sure that you leave today understanding those. Okay, so so the first bit will be things that you probably have seen before, but it's your chance to ask questions. Then I'm in the curious situation of talking about other people's work, because I don't myself work a lot in this community. Most of my research is on SDEs and SPDEs and other applications of multi-level methods. But there are a number of papers by the group at KAUST that you should be aware of, that they add extra ideas above what you've heard so far this week. And then I'll say some bits of my own thinking at the end, if there's time, which there probably won't be much of. Monte Carlo simulation is really it's a brute force. When would you do Monte Carlo? Essentially, when you have a very high dimensional problem and anything else is going to be kind of infeasible. So if you have a large number of reactions, a large number of species, that's what I mean by high dimensional problem. Because then you go to a chemical master equation and you have a large number of dimensions and you get killed by the curse of dimensionality, that the cost goes up exponentially with the number of dimensions involved. Okay? Now, the fact that Monte Carlo is brute force, traditionally it has been viewed as horribly expensive. And what I would like to get over is the idea that multi-level significantly improves its computational efficiency. The cost may still be significant, and it is possible that the cost will be too large for some applications. But that tends to be much more in the stochastic PDE setting, where each individual simulation is phenomenally expensive. In this setting, doing your reaction path networks, each individual stochastic instance isn't very expensive to compute. And so these multi-level methods really make things feasible in a way that I think previously they weren't. Okay, so this is just setting it up in a very generic way, that we have some random samples omega out of some probability space, and we're computing some intermediate solution, which in the context of this week is doing a reaction path simulation for some finite time interval. And then coming out of that, we're then interested in some output quantity or quantities. So for example, we're interested in the value, the concentration of one particular species at the final time, capital T. Or we're interested in some time average of some other quantity over the full time interval. Or in some cases, you're actually interested in the entire path evolution, and that's then getting into an infinite dimensional output. But in general, in most applications, there's just one or two outputs of interest. So generally, F is finite dimensional, and I'll concentrate on the scalar case. Okay. Within Monte Carlo methods, there's a classic approach to reducing the variance of Monte Carlo simulation. That the number of samples you need to achieve a certain accuracy is inversely proportional to the variance of the individual samples. So by reducing the variance, you reduce the number of samples you need to simulate. So the classic approach is, if you're interested in the expected value of f, but there's some other g that has a known expectation for some particular reason, depending on your application. If g is very well correlated with f, then this is what we use. That instead of just taking an average of capital N independent samples of f, for each of those omegas, we also compute the difference between g and its expected value. Okay? So the expected value of that quantity is 0, and therefore this estimator has an expected value that's just the expected value of f. But the point is that if g is very strongly correlated with f, by choosing the lambda appropriately, you can reduce the overall variance of the estimator. And so if you get the optimal value, or close to the optimal value, you actually reduce the variance by a factor 1 minus rho squared, to rho is the degree of correlation between f and g. Okay. So the multi-level method, in a sense, is a bit like this. That in a two-level method, we want to estimate some output quantity f1. But it's much cheaper to simulate some other quantity f0 using a less accurate simulation, perhaps. But f0 is similar to f1. So the expected value of f1 is just the expected value of f0 plus the expected correction. So instead of directly estimating this expectation on the left, we instead independently estimate each of the expectations on the right-hand side. So we estimate the first one using n0 samples, and the second one using n1 samples. Okay. So the difference here from the control variant viewpoint is that we don't know the expected value of f0, our control variant, so we're having to actually simulate that. Okay. Also, we're using sort of lambda equals 1 in this, but it's not worth trying to do anything else, basically. So where are the savings here? The savings come from the fact that f0 is close to f1. This difference here is a small quantity. And so in estimating that, it's got a small variance. You don't need very many samples, n1, in order to accurately estimate the expected correction. Okay. This n0 here, you'll need typically lots of samples to estimate the expected value of f0, just as many samples as you would have done to do this one. But the point is that these are cheap samples. f0 is much cheaper than f1. And so that's where it's working. We're doing lots of really cheap simulations and very few of the expensive simulations. And that's what leads to the reduction in the overall computational cost. Okay. So this is with 2 levels. We can then go to multiple levels. Okay. So we have a whole sequence of approximations, and then this is the one we're finally after, which is with a very accurate simulation, lots of time steps, for example. Okay. So on the finest level, its expected value is the expected value on the coarsest level plus all of these expected corrections, this telescoping sum. And again, each of the expectations on the right-hand side, we estimate independently using a number of samples that varies with level. So this is for that one, and then here we've got the sum over levels of independent estimators for each level of correction. Okay. But the point here is, when I say n here and n here, that's corresponding in some sense to the same underlying stochastic sample omega n, such that these two are close to each other. So there's a small variance there, and so on the finer levels, in fact, these are going to get closer and closer together on the finer levels, so we'll need fewer and fewer samples on the finer levels to get the expected correction. So if we define C and V to be the cost and the variance of these quantities, then we have a total cost that's a sum over levels of the number of samples on that level times the cost, and the variance of the combined estimator. Because we're simulating each level of correction independently, the variance of the sum is the sum of the variances coming from the different levels. And on each level, the variance of the average is the variance of a single sample divided by the number of samples we've taken on that level. So we then have a constrained optimization problem that we want to minimize the total cost to achieve a given accuracy, a given variance. Okay? So we just treat the number of samples as being real variables, although obviously they're integers actually. But treating them as reals, we introduce a Lagrange multiplier, differentiate to get the optimum, and that gives us that optimally the number of samples is proportional to the square root of the variance divided by the cost. Okay. And as we go to finer levels, the variance is coming down because there's a smaller and smaller difference, and the cost is going up. And so for both of those reasons, the number of samples comes down quite rapidly as you go to the finer levels. What's more interesting is actually the product for a particular level of the number of samples times the cost. That product then goes as the square root of the product of VL and CL. This is really showing what fraction of the overall computational cost is going into that level of correction. And here it's not clear, it's application dependent as to how this is going to behave. In what I consider the good cases, the variance comes down very rapidly, much more rapidly than the rate at which the cost increases. And so in that case, this product will come down with level. And so most of your computational effort is actually on the coarsest level of resolution. But in poorer cases, that product may actually increase with level, and so you end up with the dominant cost still coming from the finest level of resolution, but the cost is still reduced compared to a standard Monte Carlo that only does calculations at the finest level. And in fact, in the stochastic reaction network case, this product is approximately constant, and so you end up with a fairly even split of effort across all the levels of resolution. Okay, so we can get the value for the Lagrange multiplier by putting this expression back into the variance and saying that we want to have a variance that's of order epsilon squared. And then that gives this total cost, and you can contrast that to the standard cost. But basically, you always win regardless of whether this product is increasing with level or decreasing with level. Okay. My interest in this was motivated by applications in mathematical finance with SDE simulations. And with SDE simulations, the different levels correspond to how many time steps I'm using for a particular time interval. Okay? And in fact, on the coarsest level, in many applications, I could get away with just a single time step. It wasn't wonderfully accurate, but the simulation with a single time step still is well correlated with the simulation with 2 time steps. And that correlation is sufficient so that the difference has a low variance when you're looking at the difference between 1 time step and 2 time steps. And that's all you need for this to be helpful. So you don't need the coarse levels to be wonderfully accurate. They just have to be sort of vaguely representative and well correlated with the next level. Okay. The finest level depends on the discretization bias. And so that's a whole separate issue as to how fine you need to be so that the discretization bias is acceptably small for the accuracy you want to achieve. With these simple estimators, you estimate the expected difference by doing just simply 2 path simulations of the SDE with the same driving Brownian motion. Okay? And what that means in practice is that on the fine path, you're simulating a Brownian increment for each time step. If the coarse path has half as many time steps, then you just take each pair of fine time steps and you sum their Brownian increments, and that gives you the Brownian increment for the coarse time step to do the coarse path simulation. So implementing this really is a very straightforward process. And then this is a standard piece of analysis to decompose the mean square error into this piece, which is the square of the discretization bias, and then this piece is the variance we had before. So if you want to achieve a root mean square error of epsilon or less, then you can bound this by half epsilon squared, and that will determine your fineness level. Bound this by half epsilon squared, and that will give you your optimal allocation of effort across the different levels, the number of samples you need for each. There's then a theorem which is a bit of a cheat. This is a theorem that assumes lots of nice properties and then draws a conclusion. And so it assumes that you've got a sort of multi-level setup, that you have a certain rate of weak convergence, that as you go to finer and finer levels, the expected numerical approximation converges to the expected value of the true problem. On each level, the estimator has the correct expected value, so the telescoping sum works. And then this is the critical one, an assumption about how rapidly the variance of this correction quantity decreases with level. So that's controlled by the beta. And then this is an assumption about how much the expected cost of each individual sample increases with level. So beta and gamma here are the critical things. And in new applications, usually gamma, you know what that is. There are some applications where it's a bit harder. But this is the hard one usually, is working out what the right value of beta is. But given that you know what the beta and gamma are, then the theorem says that you can achieve your root mean square accuracy of epsilon with this computational cost. That if beta is greater than gamma, that's a case where the variance comes down faster than the rate at which the cost increases, then our overall cost is of order epsilon to the minus 2. And effectively, that says that the average cost of an individual sample, so averaging over all of the levels, is an order 1 cost. Yeah, and you really can't do better than that with sort of standard Monte Carlo sampling. Stochastic reaction networks actually are in the middle case, beta equal to gamma, and so you get a log epsilon squared term that comes in, at least if you're just doing tau leaping. It goes away again if we couple the tau leaping to an SSA for exact simulation on the fineness level. Challenges. It's not always entirely clear what it means to take the same stochastic sample, omega n, and to use it at 2 different levels of resolution. So each new application you look at, you have to figure out what that coupling could be. In finance, we have applications where we have difficulties because of discontinuous outputs. You can have a situation where you have a fine simulation, a coarse simulation. They're very close to each other, but then the output quantity of interest has a big difference. So in finance, we have what's called digital options that pay out $1 if the underlying path simulation is just above k, but 0 if it's just below k. And so you can get pairs of coarse and fine paths on either side of the strike k that give this big difference in output. And then doing the numeric analysis, a priori can also be tough. There's been a lot of work on this in SDEs in the last sort of 8 years. There's no time to go through this. There's lots of work on SPDEs, stochastic PDEs. The savings are often bigger with the SPDEs because with PDEs, the computational cost goes up more rapidly as you refine the grid, because you're refining it in each direction of the grid. Okay. This is just to give you a feeling that multi-level is being used in lots of different application areas. It's not just in stochastic reaction networks. There's a lot of literature out there. Use of conditional expectations. This is the trick that we use to cope with these discontinuous problems. I'll probably just skip through this, but look at the papers if this is something that's of interest to you. Okay, and skip that. Okay, so let's now look at the stochastic chemical reactions. So this is the notation that Dave was using in his lectures earlier in the week, that we've got this vector of population counts of the various species, and then it's evolving in time with a sum over the different reactions of these unit rate Poisson processes yk, controlled by this internal time sk, which is an integral of the propensity function over time. And then the zeta k there is giving the vector of changes to the population with each reaction that occurs. Okay. So you've got exact simulation methods like the SSA algorithm, which do the reactions one by one, exact but very costly. Okay. Then you have tau leaping, which is equivalent in the sort of SDE setting to doing the Euler-Maruyama method, where you freeze the propensity functions at the beginning of each time step, and then what we need is just to sample from the Poisson process for that time step. You've got now an assumed approximated constant reaction rate lambda k, and so over the time step we need to sample from a unit rate Poisson process for a time value of lambda delta t. And that gives us the number of those reactions that takes place. Okay. So Dave and Des developed this really elegant way of coupling between the coarse and fine paths. And this is a case where a priori it's not at all obvious how to have in some sense the same stochastic sample for the fine and coarse paths, so that the difference between the two simulations is small. And the crucial observation is that with Poisson processes, if you take a sample from a Poisson process of duration t1, and that you add that to a sample from a Poisson process with duration t2, then that's equivalent in distribution to taking the sample from a Poisson process of duration t1 plus t2. Okay. So what do we need to do? So I'm assuming here we're going in powers of 2 with a number of time steps. So on the top here, we have a coarse time step that really should go sort of in one step from here to here. And so what we want is a Poisson random variable corresponding to time step lambda times delta t for the whole time step. But by this, we can decompose that lambda for the whole time step into, sorry, y for the whole time step into a y for each of the half time steps. And in distribution, that will be identical. So we need, therefore, a Poisson random variable for the first piece and a Poisson random variable for the second piece. Now that's for the coarse path. The fine path, meanwhile, it needs a Poisson random variable for its first time step with a slightly different lambda, and then one for the second fine step, again with a slightly different lambda. So let's look at coupling these two here. That if we take the case where the lambda f is less than the lambda c, then the lambda c, we can decompose that as being the same y that we use for the lambda f plus the lambda of the difference, so the y of the difference in the lambdas times delta t over 2. So that's equivalent in distribution. And so the idea is that the Poisson random variable that's used for this one gets reused up here, and then you just add to it an additional Poisson random variable corresponding to the difference in the two lambdas. And then vice versa if they're the other way around. Okay? And so this leads naturally to a strong coupling between the fine and coarse paths. Okay, so the work at KAUST. Okay, so there's a major group there working on a variety of things in multi-level, but including stochastic reaction networks. So just to mention 4 papers. First couple of papers were to do with using adaptive time steps to control the probability that with tau leaping, you end up going into negative population densities. Because with tau leaping, you're freezing the propensity functions at the beginning of each time step. There will always be a non-zero probability that you end up with a Poisson change such that if you have a reaction that decreases any of the population counts, if you take a large enough Poisson variable, it'll drive those negative, which shouldn't happen. It wouldn't happen with the exact algorithm. So for example, if we have just a death process, A going to 0, and suppose our time step corresponds to the average time for a reaction to take place, then a Poisson process will give us 0 with this probability, 1 with that probability, more than 1, sorry, that should be strictly greater than 1, with that probability. So in this case, if we're starting from a population of 1, which I forgot to say here, if we're starting from a population of 1, this is the probability that you're driving the population negative. Okay, this is the probability that you go nicely from population of 1 to population of 0. And here, it doesn't change, and so you then take another time step to see what happens. So essentially, the ratio of that one to the sum of those two is the probability that you end up with a negative state. So with this death process, if you keep using tau leaping down to the point where the time step is of the order of the average reaction time, there's a high probability you'll end up in a negative state. Now, how much that matters, I think, depends on what output quantity is of interest to you. The analysis in Dave and Dez's papers looks at output functions where you're looking at the expected value of some smooth function of the terminal value. And in that case, the analysis shows that the fact that some of them go negative doesn't affect the variance of the problem, and the multi-level still works. But if you have an output which is maybe much more sensitive to what's happening with close to 0 density, so if you're looking at the probability of extinction, for example, then that might adversely affect the variance. And so these papers, they were looking to control that. And so there's a Chernoff bound that can be used to control the probability of exiting the domain. And so that controls the maximum time step so that you control the probability delta of exiting the physical domain. Yes, you can also look at the cost of doing the exact method compared to doing the tau leaping. And once the exact method ends up being cheaper, well, you switch over to using that instead of tau leaping. Okay. Whereas in the original work that Dave and Des did, they had lots of levels that were tau leaping, and then finally they had a level where everything was exact, and then they coupled those final two levels. This is much more sort of adaptively deciding on a time step by time step basis whether to do tau leaping or exact. And so in paper 2, they then extended that to doing the multi-level treatment based on that. Yes, and it gets a little bit trickier when they're then coupling the tau leaping with the exact simulation, but that's fine. So look at those papers for the details of that. Paper 3 addresses the issue that in some applications, you've got some reactions which are firing a lot, some reactions which are firing very infrequently. And so it makes sense to sort of split them up and decide which ones to model using tau leaping, the ones that are firing a lot, and the ones that are firing very infrequently, you can use the exact simulation method to compute those ones. Okay, and that can give you some significant benefits, at least in certain cases. The idea is simple. The implementation gets a bit harder to work through. Oh, there's also a very nice idea on an extra control variant for the courses level of simulation. So in the courses level, we've got this approximation using tau leaping with large time steps. Okay. The idea then is to use a control variant equal to this. So here we've got the true sort of internal time based on the evolving population counts. Here, this S hat is a deterministic approximation to Sk. It's basically taking the expected value, which then satisfies ordinary differential equations of decays exponentially in time in many applications. Okay. So the timing is basically a deterministic thing, but then you have the Poisson process being applied to that. And so the idea is that these two will use the same Poisson process, but different internal times. And this one, you can work out the expected value of output functionals from this. And so that's what's very nice about this as a control variant. So you first solve an ODE to get this sort of approximate state, S hat, and then do the coupling for the same Poisson processes. So you first do the tau leaping simulation, and then doing the tau leaping simulation, you're sampling the Poisson process at a certain set of internal times. And then for the other one, you need to know its Poisson value at a different internal time. So if that internal time is less than the final internal time you needed for the regular simulation, then it lies between two Poisson values, and you do a Brownian bridge or a binomial bridge to get that intermediate value. And if it lies beyond that, then you just have an extra Poisson increment to go up to this new time, S hat. Again, look at the paper to see the details. Finally, there's a new paper just out, well, still an archive paper at this stage, on looking at drift implicit methods. So tau leaping, if you have an application where you have a forward-backward reaction with incredibly large reaction rates, you have this sort of dynamic equilibrium being set up. Something where sort of A goes to B and B goes back to A with high rate constants. You end up with this sort of dynamic equilibrium between A and B. But because of the high rates, this is a really stiff problem. And with explicit tau leaping, you would have to use very small time steps for stability. And so that limits the savings you can get with multi-level, because you'd like to be able to go to very large time steps on the course levels for computational efficiency. But if it's unstable, you'll basically get garbage. It won't be a useful control variant. So, so this sort of situation really hits the efficiency of multi-level based on explicit tau leap. By going to implicit tau leap, you're able to use much larger time steps to cope with these fast forward-backward reactions. But the implicit tau leap does involve doing a small Newton iteration. There's a nonlinear step in there. And so there's additional computational cost that comes from that. And so there are trade-offs. So for some applications, it's definitely beneficial, but you wouldn't want to perhaps use it all the time because of the additional cost per time step. Okay, some other quick thoughts. The splitting, or the coupling that Dave and Des has is really elegant and really works well in practice, but it's not the only possibility. And so just in terms of talking about multi-level, the concept doesn't prescribe for each new application exactly what the coupling has to be. There's a lot of flexibility that you as algorithm designers have to choose alternative couplings. What you do have to make sure is that you respect the telescoping sum. So the telescoping sum, you have the sum of expected corrections. And what we need to make sure is that the PL here and the PL here, they're showing up in two different levels of correction, but they need to cancel out in the telescoping sum. And so they essentially have to be the same expected value. So respect this telescoping sum and then try to minimize the variance, so you reduce the number of samples you need. Two other possibilities then, just to illustrate the ideas. One is having the same unit rate Poisson process, and another is using the inverse Poisson CDF. So just quickly, the same unit rate Poisson process follows on from what I was describing with the control variant discussion. That you basically keep track of the unit rate Poisson process being used for, say, the fine path, and then when you do the coarse path simulation, conditional on what you already know about the unit rate Poisson process, you have to sample at additional internal times within that. And so this is where you get the binomial bridge, that if you already know the value of the Poisson process at times t1 and t2, if you need it at some intermediate time, then you have to get that from a binomial bridge. The other one is a standard technique in random number generation, that for any continuous random variable capital X, the cumulative distribution function as a function of little x is the probability that capital X is less than little x. And if you apply that cumulative distribution function to the random variable x, capital X, that gives you a uniformly distributed random variable. Okay, essentially, if you have a population of people in the country, what's the probability that picking a person at random that they're in the oldest 1%? Well, it's just 1%. The probability that they're in the middle 1% is just 1%. So you can generate random values x then by taking a uniform random number between 0 and 1 and then inverting the cumulative distribution function to then give you your random variable capital X. So it's a general technique. So here, what could we do? Well, we need two different Poisson variates with slightly different lambdas. We can generate the same uniform random variable u and then invert two slightly different CDF functions to get the Poisson random variables we need. Okay. And it turns out it isn't too difficult to actually do that. I've developed software for inverting the Poisson CDF. In practice, it doesn't cost much more than inverting a normal CDF. However, a student tried this out to see if it would lead to a better coupling, and it gave almost the same variance as using Dave and Dez's treatment. So in this application, there's no benefit from doing that. But it's just to really highlight the fact that there is flexibility on how you do this coupling between coarse and fine paths. There isn't necessarily just one right way of doing it. Okay. Conclusions. So the basic idea is incredibly simple. It is being used now in a wide variety of applications. I think actually reaction networks are one of the areas where you get the biggest savings because the cost of doing the exact SSA is just so expensive. You have so many reactions that looking at any new application, you want to know what's the ratio of the cost of the finest simulations you're likely to need versus the coarsest simulations that are vaguely representable of the true problem. And so compared to doing thousands of reactions on the finest level versus maybe 10 big 10 big tau leaping steps on the coarsest level, that's kind of the ratio of savings you're likely to achieve. On my web pages, I've recently done a 70-page Acta Numerica review article on multi-level methods. So if you're interested in learning more about multi-level, that's a good place to start. I've also got web pages where I've got code available. Actually, right now it's MATLAB and C++. Someone's helping me do Python versions, and that will be up there in a little bit of time. And that's just a list. Unreadable, I know, but these are just different groups in the world working on multi-level in a whole variety of different contexts. So there's a lot of activity going on. And if you go to my community web page, you can see all the groups, all of the papers that they're working on, so categorized by application area. Okay, and there I'll finish, and hopefully I've left some time for questions.
Thank you. So any questions? Linda?
So with this regard to the negative concentrations, it's in my opinion, the problem is not so much that they're negative and unphysical, but that it's quite easy for many of those chemically reacting systems to go unstable when a concentration becomes negative, and then the solution paths would diverge from each other forever on.
Okay.
It's hard for me to imagine how that wouldn't be a big problem.
I'll jump in on that.
Yes.
So in practice, when I when I splash tau leaping up there, I just splash tau leaping. I don't say what's actually going on when these certain circumstances come in. So what my actual approximate process typically is if something goes negative, here's a choice. You make the choice. Either set everything to 0 for that point forward, okay? Forever.
I see. Okay.
Or
Yeah.
pop it back in with some reflection. Okay? You make a choice. I don't care what you choose.
Okay.
The point is
It doesn't matter that it's not.
It doesn't matter.
Yeah.
We couple it with the finest level. So no matter what you choose, it's unbiased.
Okay. Perfect.
Cannot go wrong.
Perfect.
And it's quite stable.
So simply an issue of what's the variance. Does the variance suffer or not?
And so exactly. So it's just a question of how do you define your intensity functions when you go negative. And as long as you don't do something that makes it blow up by square, these intensity functions, then you're 100% safe.
Okay, I wish you would have said this years ago.
Okay.
It's the dirty little details that matter. Yeah.
In each of the paper, there is a line.
Yes, I have read it. I can testify to that. Yeah, because for the numerical analysis, I think you just set it. You set the rates equal to 0 from that point on.
Well,
for that reaction.
Smoothly go to 0, and so that I get derivatives and stuff. But yeah.
Oh, okay. Yeah.
So, I mean, we've seen a lot on multi-level Monte Carlo as far as the time discretization goes, but you've made allusions a few times to SPDEs, where then you would have different spatial resolutions. Is there anything particularly challenging or worth noting about kind of doing multi-level Monte Carlo with spatial, from the spatial standpoint?
No, I mean, with SPDEs, it's really pretty natural, I would say. So, the most work's been on elliptic SPDEs, where the stochastic bit's coming in through the coefficient fields for the diffusivity. And there, you simply, refine by factor 2 in each direction as you go down through the levels, and you have to have a way of simulating instances of the stochastic coefficient field, and then you have those on the coarse grid and the fine grid. And that all works fine. There's been some amount of work. I mean, I've done a little bit myself on things where you've got parabolic equations with white noise, so the spatial temporal white noise being fed in as a forcing term, and again, there are some slight subtleties in exactly how you set up the coupling between the fine and coarse levels. But I would say that's relatively straightforward. Yeah.
I think it's similar. So if you do it not just for reactions but for the RDME, and then you have, like, could you do multi-level Monte Carlo for the RDME where you have space distribution,
Right.
and then the levels would be the different ones, and at some point you go to Brownian dynamics or something.
In principle, yes. Yes, I missed the spatial lecture. I'm having trouble sort of specifically commenting on how this would work.
Maybe
But I mean, the natural thing is just to have a geometric sequence of grids. Yeah.
Yeah, I mean, we've been trying to do it for the RDME just in one dimension with just diffusion for quite a while. In theory, it's perfectly possible, but actually finding a good coupling between levels is very difficult. We've tried quite a lot of things, allowing particles to jump different distances, trying to couple right jumps with other right jumps on different levels. In practice, it doesn't seem to work out yet. That's not to say it's impossible, but we haven't come up with a good way of doing it, and we've been trying for a year. Yeah, it's the coupling.
Yeah, I think you want to respond to the negative issue.
Yeah, it also allows you to use to start with coarser grids if you control the exit. Like otherwise.
Okay, so you can go to much coarser grids without worrying about.
Otherwise, the estimation in the coarse level is very bad, and then you start with a bad estimation and then coupling. Usually, you don't get a good estimation at the end. This is small.
Yeah. So some of these things are so application dependent. Depending on which example you use, there are different pros and cons.
So I guess.
And so it's good for users to be aware of all the different possibilities, and then they'll have to think about their own applications as to.
But it allows you to start with a good level C.
How accurate is how?
Okay.
So, but asymptotically it won't make a difference, but in reality, you say in practice it would make a difference, sort of. I mean, if you were to set epsilon to 0 in the normal MLMC, because epsilon.
But still, for some problems, even if you go to 0, the size of the time step, you need to start from a very fine level, even finer than the exact.
No, I'm not talking about the time step. I'm talking about the mean square error. So if you asymptotically, if I understand correctly, having heard you giving all these talks, in terms of if you take epsilon to go very small, in terms asymptotically, where you start.
Asymptotically, all these methods have the same dependence in epsilon in terms of the exponent. It's all about the constant out front. Yeah. So. Yeah. So. And I think it just varies depending on the test example that people are looking at. So there's basically a whole toolbox of different things that can be brought into the code, and then there's the issue of how many of these you want to simultaneously have in your code, and just manage the complexity of that. But.
I have an offer for the tuliping community actually. If we have a domain with a small hole that we have discussed for the last 3 hours, is it possible to find out, use this algorithm to estimate first passage time? Because we are restricted, of course, by the size of the hole. This should give a constraint. Is there a possibility to go in that direction?
So there are some people who are now looking at multi-level in the context of rare event simulation. So those are people who are particularly interested in, say, engineering systems and safety analysis and stuff. That just taking what's being worked on currently with stochastic reaction networks, wouldn't work. Well, I guess your problem's an SDE problem. Well, taking what's currently in the literature for multi-level applying to SDEs wouldn't be terribly efficient for your problem simply because of this problem of hitting the hole. I mean, to some extent, also, you're looking at problems in sort of 2D, 3D. My instinct for those would be to use, the PDE approach and go with finite element methods. I mean, generally, I would say to people that the trade-off between SDEs and solving the PDE is in dimension 3, I would still be going with PDE. And dimension 5 and above, I'd be going with SDEs. And dimension 4 is kind of the borderline. So for that application of yours, my instinct would be to go with adaptive finite element methods, where they'll adapt into the neighborhood of the hole. Sorry.
Well, you could just use delta t to define your levels.
Yes, the problem with doing Monte Carlo simulation for that hole problem is the probability of hitting the hole is so small that that will kill the efficiency of the method. I mean it's even worse than the problem that I was talking about digitals with discontinuous behavior. So it wouldn't be a good methodology, for doing the small hole escape problem.
Are there any other questions? Okay, let's thank Mike again. So what I would like